Hello, this video is for section 2.3, which is called Rates of Change, Velocity, and Marginals. And there isn't really anything new here in terms of calculus rules, but we're pausing for a little bit to just understand how calculus fits into certain kinds of problem solving. So one thing we want to recall is that if we have a function, we can measure its average rate of change, very often abbreviated as AROC, AROC. And our formula for the average rate of change on some interval from x equals a to x equals b is that it's the change in the value of the function divided by the change in the variable. So specifically, it looks like this. F of b minus f of a, that's measuring how much f has changed, over b minus a. You've seen this formula before. So let's look at a quick example. Suppose we have an object that's dropped from a height of 100 feet. So here, oops. So there's the ground. Maybe it's dropped from some platform and it falls down. So based upon how gravity works, we can come up with a pretty good formula for the height of this object after a certain amount of time. So after t seconds, its height measured in feet would be given by a formula like this, negative 16t squared plus 100, and that's a valid formula until it hits the ground. We're just going to point out that the variable here is called s. That's very commonly used to indicate a height or position, I think because of a Latin word that starts with s, but it's just sort of a tradition. And what we're doing in this formula is we're ignoring air resistance because that makes the formula much more complicated. We'll assume there isn't much air resistance, and so this is pretty much the correct formula. So the rate at which a position changes, the rate of change of position, is called velocity. Okay, so velocity is just our name for the rate at which position is changing. It's very similar to speed, if that's a more natural word for you. So we want to find the average velocity of the object on the interval from t equals 2 to t equals 3. Right? So basically, if I were to start my stopwatch when it says exactly 2 seconds, and I end my stopwatch when it says exactly 3 seconds, what was the average velocity over the course of that interval? So average velocity is an average rate of change. And velocity is a kind of rate of change. So average velocity is an average rate of change. So here our function is called s rather than f, and our variable is called t rather than x, but it's the same pattern. We would be computing what is the position at time 3 minus the position at time 2 over 3 minus 2. I'm just going to write that clearly. Right? I recommend just show how you're using the formula first. Here I am demonstrating that I know how to use the formula. Now on the side, I will compute these things. So S of 3 Okay, I am going to modify something here, and by the time, so I apologize, let's change this to 200. I will change it in my document. By the time you're taking notes, you'll notice it already says 200. Sorry about that. So S of 3 would be negative 16 times 3 squared plus 200. So that's negative 16 times 9 plus 200, which is negative 144 plus 200, which is 56. So I was noticing I was about to get a negative number. So basically, it's starting at a height of 200 feet, and it's at 56 feet when the clock says exactly 3 seconds. S of 2 would be negative 16 times 2 squared plus 200. Which would be negative 16 times 4 plus 200, which is negative 64 plus 200, which is 136. So after 2 seconds, it's at a height of 136 feet. Okay. It's higher at the beginning because it's falling. So here, if we plug these in, we would have 56 minus 136 over 1, which is negative 80. And our units here would be feet per second. It's a rate, so it has a per in it. And the reason why it's negative is because the height is getting smaller. Velocity can be negative. It means that your position is getting smaller, right? And it's the height, right? The height is getting smaller because this thing is falling, right? That is our average velocity between when the stopwatch says exactly 2 seconds and when the stopwatch says exactly 3 seconds. So this is something you've seen before. Now, in a lot of cases, things do not change at a steady rate. For example, gravity makes things accelerate as they fall. If something is falling over gravity, right, here's the slow-mo. Right, if originally it's falling slowly, and then it starts to fall faster, and then it falls faster and faster and faster. Right? If there's a lot of air resistance, it stops speeding up. But at least over the course of the first couple of seconds, if you slowed down the video, you would notice, oh yeah, it actually is speeding up over the course of those first few seconds. So sometimes we don't want to talk about an average rate of change or an average speed or an average velocity. We want to talk about it being instantaneous, right? At some very specific moment in time, or at some position, or in some situation, right then, right? Not on average, but right then, how fast is something changing? That's called an instantaneous rate of change. And the good news is we already know how to do this. Instantaneous rate of change is just the limit of an average rate of change. It's the limit of this change, of this rate of change in f over change in x, which would look like this, which is a formula we've seen before, which is just what the derivative is measuring. So I'm not going to go through all of this in detail. We really just want to file away. The derivative measures the instantaneous rate of change. This is something that I showed you before, and we really want to come back to it, right? We have the derivative, which we think of as an algebraic formula that we calculate. If we are applying this to a graph, the derivative measures slope of a tangent line. Right? That's the meaning of this when we're looking at a graph. But if we're just describing some sort of phenomenon where something is changing, it represents an instantaneous rate of change. Right? That's when we're just applying this to a phenomenon. If I am observing something there in the world that is changing and I want to know the rate at which it's changing, these are all basically the same. And we want to be comfortable moving throughout this diagram. Sometimes to understand slope of a tangent, we need to think about it as a rate of change and vice versa. Sometimes to figure out slope of the tangent, we need to get that formula for a derivative. Sometimes to think about instantaneous rate of change, we have to get that formula for a derivative. But they're all doing the same thing, just in different contexts. So let's go back to our previous example. And again, let me change this to a 200. By the time you're looking at this in your notes, this will already be changed. So let's find the instantaneous velocity at t equals 3 and the instantaneous velocity at t equals 2. And let's see if those make sense. So here's the good news. We know that instantaneous velocity is the same as an instantaneous rate of change, which is the same as a derivative. So we had this formula, f as a function of time is negative 16t squared plus 200. So velocity as a function of time is just the derivative of that. And we've already started learning all these great shortcuts. We don't need to do a limit. So the derivative here would be negative 16 times our derivative of t squared, which is 2 times t, plus the derivative of 200, which is 0, which works out to negative 32t. So at t equals 2, the instantaneous velocity would be negative 64 feet per second. When the stopwatch says exactly 2 seconds, the object is falling at a rate of 64 feet per second. Right? The negative is included in the sense of me using the word falling. at t equals 3, we would plug in 3 and we would get negative 96 feet per second. We saw on average it was 80. And it's just a coincidence that that is literally the average of these two numbers. Don't read into that too much. That's going to be different in other cases. But what definitely makes sense is this thing is speeding up. When the stopwatch said 2, it was moving at a rate of 64 feet per second. When the stopwatch said 3, it was moving at a rate of 96 feet per second, basically 50% faster. So it makes sense that the average is somewhere between those two. It's not necessarily the literal average in every case, but it certainly makes sense that if something is speeding up, then its speed at the beginning is smaller than the average, and its speed at the end is bigger than the average. All right, now just a little more application here. So physics and engineering is where there's a ton of applications of calculus. It's why calculus was invented. But aside of that, we see a lot of examples in business and economics. Right? A lot of analysis of products and money and economies and things like that can be done through the lens of calculus. And just a bit of vocabulary. In the language of economics, right, when people are talking about economics and business, usually an instantaneous rate, they don't use that phrase. Instead, they call it a marginal rate. Right, so the idea is a margin kind of we think of as, kind of the extra. Right? On the margin of your paper is that extra space on the side. We're thinking kind of, what's happening if we go a little extra? Right? I'll try to make sense of that in a second. But you can just say, oh, marginal is basically business speak, economic speak for instantaneous rate of change, which of course is a derivative. Right? So just as a concrete example, maybe we have a cost function. Some function is measuring how much it costs a business to manufacture a certain number of units. So that instantaneous rate of change, same as the derivative, would often be referred to as the marginal cost. Right? Marginal basically is just this word that means derivative, means instantaneous rate of change. So let's look at an example. A company sells alarm clocks, and their profit in dollars for selling X clocks is given by this function. So first, we're going to find the average profit per clock if 100 clocks are produced and sold. So P of 100, I'll just plug that in. So there's a bit of a computation here. You can just trust me on this. This would be 0.002 times 100 cubed is 1,000,000. This is 1,000 over here. 0.02 times 1,000,000 is 2,000. So we get 3,000. Right, so what this means is if we are making 100 clocks, there's $3,000 of profit. So the average would be 3,000 divided by 100, which is $30 of profit per clock. Right? I can only assume these are very fancy or specialized alarm clocks. Don't worry about that issue. Right? We're just pretending that these are expensive alarm clocks. And so this company, on average, will make a profit of $30 per clock. Now, let's talk about the marginal profit when the production level is 100 clocks. So remember, marginal is basically just business speak for derivative. So I am going to compute the derivative of this function. And I know all these shortcuts. I have this number, 0.002. Derivative of x cubed is 3x squared. Derivative of 10x is 10. So this works out to 0.006 x squared plus 10. And if I plug in 100, I would get 0.006 times 100 squared, which is 10,000, plus 10, which is 60 plus 10, which is $70 per clock. And now in C, we want to explain what are the different meanings here and why are these different numbers. So we need to understand that one of these is an average and one of these is instantaneous. And something you probably believe already, even if you haven't studied business in detail, is that generally speaking, the more you make of something, the more efficiently you can do it. Right? It's harder to make 100 clocks than to make one clock. But by the time we get to that 100th clock, probably we're doing it more efficiently. So here's kind of the idea. So this is one interpretation. And I'm not expecting you to have exactly this sentence, but the first several clocks are probably expensive to produce, leading to a low profit. But eventually, as we keep making more clocks, we do it more efficiently. So if we're doing it more efficiently, we can probably make a bigger profit. Right? If I can make the clock for less money, then I get more profit when I sell it. So these expensive clocks get factored into the average profit of the first 100 clocks. Right, so of those first 100 clocks, the early ones were probably very expensive. So I probably wasn't making much profit on those. But as I make more and more clocks, I get more and more efficient. The marginal rate is basically, going back to that thing before, is extra. So the marginal rate is only focusing on the extra profit when we're already at a level of 100 clocks. So the marginal rate measures the extra profit of one additional clock, right? And you can interpret it two different ways, right? There's a little inefficiency here, but either you could interpret it as to go from 99 clocks to 100 clocks, or to go from 100 clocks to 101 clocks. It'll be roughly the same number. You can basically think that when we're at this level, the interpretation is we get $70 of extra profit for one extra clock. This is not an average. We're not even thinking about those expensive ones from the beginning. We're already at the point where things are going efficiently. So if I'm already at 100 and I'm doing things well, I'm just saying, what is that extra profit for one more thing? That's 70. Okay, so this is very different, thinking about an average, including all of them, the expensive ones as well, versus marginal. Very often people talk about marginal. If you ever hear information about tax rates are often talked about in terms of the marginal rate. Okay, so I'm just adding a little bit. If you hear something about like, oh, there's a 35% tax rate, that probably doesn't mean that your tax is 35% of your income. It probably means that that's your marginal rate. If you make one extra dollar, your taxes go up by 35 cents. But it's not necessarily saying that you're paying on average 35%. In America, we have kind of this tiered tax system. Your first amount of income is totally free with no taxes. Then a certain amount is at a low tax rate. And the more money you make, the extra dollars are taxed at a higher rate. But a marginal tax rate of 35% is not the same by far as an average tax rate of 35%. Okay, so just keep in mind this word marginal means extra, or in the language of calculus, derivative. All right, that's it for this video.